All right, today's starter is the following. We have a car, starts from rest, and accelerates at a rate of 4 meters per second every second for 20 seconds. Draw a kinematic stack. So there will be a problem on the exam just like this one. Okay? So now I always like to start with the kinematic stack where I kind of draw out the velocity, the position versus time, velocity versus time, and acceleration versus time graphs ahead of time. Although, look at this. Since I know starts from rest and accelerates at a rate here for 20, so everything's going to be positive. I'm going to assume that the car is starting at 0. It didn't tell me that, so I'm going to assume that. And it's okay. You can do that sort of thing. Hey, let's just say the origin of my position graph is when we start. Now, I could have told you in the problem, hey, a car starts at a position 20 meters from the origin and blah, blah, blah. So, okay, well, we've got a starting position. And then, but if it's accelerating forward, that means that the position is always going to be positive, the velocity is always going to be positive, and the acceleration is given to be positive. And that's why I drew my graphs like this. If you don't know, you can always draw your graph like if you're going to have a negative velocity or a negative position, you can always draw your graph, a real kinematic stack, you ought to start it like this. And of course, if it's a stack, that means the vertical axes for position, velocity, and acceleration, these are all lined up. And then your time axis is identical, okay, as you go across. But I like to start with the easiest one, so let's do that. The acceleration is 4 meters per second every second the whole time. So we have 20 seconds, so let's just go 5, 10, 15, 20. Is that legal? Yes. Some of you want to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can do that, but I'm lazy. All right, so there's my time axis. Let me zoom in so you can see it a little better in the back. Oh, this camera's getting slower at focusing. Kind of like me. All right, so it's 4 meters per second, so we're going to go 1, 2, 3, 4. And it's just 4 meters per second the whole time. And there you go. So if you did this on a test, you get 100% on the acceleration graph. Why? Because I incremented the time axis and I labeled it with the variable name and the units. Same thing with the vertical axis. Scaled it properly with this. All right? 100%. Now, let's think about velocity. There's a couple ways of doing the velocity graph. I'm going to work my way up. Sometimes you work your way down, sometimes you work your way up. Let's work our way up. What do I know? What is the area underneath an acceleration versus time graph? Well, this area, anybody know? Yeah. Change in velocity. So we went 4 meters per second every second for 20 seconds. So that means I started at 0 velocity. That was given. V naught equals 0. Right? Because it said in the problem it started from rest. Starts from rest. That means V naught equals 0. And then it changed its velocity. By how much? Well, 4 meters per second for 20 seconds, or 4 meters per second every second for 20 seconds gives 80, right? 4 times 20 is 80. 80 meters per second. So that means if I start from rest, my change is 80, so my final velocity is 80. So let's do 5, 10, 15, 20. And at 80, so I'm going to go 20, 40, 60, 80. And I know this is a straight line, right? So I'm going to go here. And then if I had a ruler, I would do this with the ruler, but I'm just going to do it freehand. Straight line. Now, that's one way to do it, because look, the acceleration is the slope of this line. And if you just pick 2 points on this line, well, if this is 5 seconds, and what's the change? Well, you're going to go from 20 to 40. So that's a change in 20 meters per second. You do the math. Delta V over delta T is my acceleration. 20 meters per second divided by 5 seconds is 4 meters per second every second. 4 meters per second squared. Yes? Any questions? You behind? You ahead? How you doing? Okay. There's another way of doing this, of drawing this graph. You can use the first kinematic equation. V equals V naught plus A times T. Well, let's see. V naught is given to be 0. And then you have A, and this, so now it's just A times T, which is what we did here, A times T, the area of that graph. And so that's going to give you the, so you just plot, you can plot points here and do it, but you get the same thing. Right? Because constant acceleration motion assumes that the velocity as a function of time, we're assuming a constant acceleration, which means constant slope, which means velocity as a function of time will be a straight line. Okay? Cool. Now we get to the hard one. Now, I need to scale this. So what's my maximum position going to be? Well, that's kind of hard. But there's a couple of ways we could do it. What's the area underneath this graph represent? What's the area underneath a velocity versus time graph? What does that represent? Change in position. Delta x, displacement. But now we have a triangle, don't we? So we have 20 times 80. Yikes, what is that? 20 times 80, that's 1,600. Is that right? 1,600. But what do we have to do to that 1,600? Because what shape is this? It's a triangle. Triangle is half of a rectangle, isn't it? So we have to cut it in half. So I can cut it in half and I get 80. Or I'm sorry, 800. 800. So I know that my maximum position is going to be 800 meters. So I'm going to scale this for 800. So 100, 200, 300, 400, 500, 600, 700, 800. Look at that. I'm a machine. I know just how to do that. All right. So I'll just go 200, 400, 600, 800 meters. So we know that, and I'll do this 5, 10, 15, 20. Okay? And we know that at 20 seconds now, we have determined that my position will be here. Now, can I do what I did with velocity versus time? Can I just draw a straight line? Well, you could, but you'd lose points. Because look, at first it's going slow, so it's not changing its position by very much. But then, now it's going faster, so it's changing its position greater for each unit of time. And then, the last 5 seconds, it's really moving fast, so it's changing its position by a lot per unit time. So there's a couple of ways to do it. I'll tell you what, let's do 5, 10, 50, and 15. Let's just do the same thing. Oh, what's the area of this little rectangle or triangle right here? Well, what's 5 times 20 divided by 2? What is that? 5. What's 5 times 20? 100 divided by 2? 50. So my position at 5 seconds, so I'm going to go up like here, is going to be 50. Well, here's 100, so 50 would be right here. So it didn't, on this scale, it didn't go up very much. Now let's do the same thing at 10 seconds. What's the area under my velocity versus time graph at 10 seconds? Well, 10 times, what was it, 40? 10 times 40 is 400 divided by 2, 200. It's right there. Now let's do 15. So at 15 seconds, what is this, at 60? Okay, you can figure it out. You can put 15 in here. 15 times 4 is 60. Yeah, 60. So what is 15 times 60 divided by 2? So 15 times 60 divided by 2. Well, that's 30. 3 times 15 is, so what do you get? Huh? 400? 450? Yeah, 450 what? Meters? Okay, so where's 450? Okay, here's 400, here's 500, so 450 is right there. And look at those points. Isn't that nice? What happens when I draw? Don't draw straight lines. Don't connect the dots like you're playing, some child's game. You want to make a nice curve. Sweet. Okay. Now another way of doing this, instead of doing these areas, you can use the third kinematic equation. You could say delta x equals v naught t plus 1/2 a t squared. Right? And so, well, v naught is 0. And let's say that delta x is, well, that's x minus x naught, but x naught is 0. So really, this is x equals 1/2 at squared. Well, let's say for 1/2, 4 meters per second every second. Let's put in 20 seconds. And I'm going to square it. So what is 200? Oh, sorry. What is 200 squared? 20 squared is 400. 400 times, well, 4 divided by 2 is 2, so 2, it's 800. Ooh, yeah, that worked. You can plug in any value for time you want. Well, let's put in 5 seconds. What's 5 seconds squared? 25. What's 25 times 2? It's 50. It's just what we got with the area. So you can do it either way. Isn't that awesome? Well, I think it is. But I'm weird. Zoom out. So on the exam, I'm going to give you a problem like this, and I'm going to ask you to draw the position, velocity, and acceleration graphs. Okay? And or I could give you a velocity versus time graph and ask you to draw the position and the acceleration and ask you questions about it. There's a lot of variations on this. Okay. Make sense to everybody? Any questions? Seriously, any questions? Yeah, okay. That is all.